This video covers Part 2 of Section 3.10 Epsilon Delta Proofs. In this video, we're going to look at how you prove that a sequence converges. Let S sub n be a sequence and S be a real number. To prove that the limit as n tends to infinity of S sub n is equal to S, we need to prove the statement in the definition. For all epsilon greater than 0, there exists a capital N in R such that for all little n in n, little n greater than capital N implies the absolute value of S sub n minus S is less than epsilon. Here are the steps involved in the proof. First, since the statement starts with a universal quantifier, we start with a proof by arbitrary element. So we'll suppose epsilon greater than 0 is an arbitrary positive real number. We next need to prove the existence of a real number capital N in R with the property that for all little n in n, n bigger than capital N implies S sub n minus S is less than epsilon. As in any constructive existence proof, there are two parts to this proof. First, we need to find a real number capital N. We usually need to use the condition S sub n minus S less than epsilon to determine what we should choose for capital N. We usually work backwards from the conclusion S sub n minus S less than epsilon to determine an inequality of the form little n greater than capital N. We may also have to make some preliminary assumptions about little n in order to simplify the calculations in this process. This probably doesn't make a whole lot of sense right now, but once you see some examples, you'll sort of see what this is referring to. The number capital N will in general depend upon epsilon. However, since the quantifier for capital N comes before the quantifier for little n in the statement being proved, then the same capital N must be used for all little n, so capital N cannot depend upon little n. Second, we have to verify that our choice for capital N satisfies the two properties. The domain, capital N, is supposed to be an element of R. The domain requirement usually follows immediately from the choice of capital N. And our propositional function, which is for all little n in n, n bigger than capital N implies S sub n minus S is less than epsilon. This is another universal statement, so to show this, we use a proof by arbitrary element combined with a direct proof of the conditional propositional function. So we'll suppose little n in n is an arbitrary natural number. Suppose the hypothesis, little n is bigger than capital N, and we need to show that this implies the conclusion S sub n minus S less than epsilon. For an example, we'll consider the sequence in the previous examples. Let S sub n be the sequence defined by S sub n is equal to 1 plus minus 1 to the n divided by n for each n in n. Now intuitively, we know that our limit for this sequence is 1, and so in this example we want to actually prove using the definition that the limit as n tends to infinity of S sub n is equal to 1. To do this, we need to show the statement in the definition is true. For all epsilon greater than 0, there exists a capital N in R such that for all little n in n, n bigger than capital N implies S sub n minus 1, which is our limit, is less than epsilon. So to start the proof, we're going to suppose epsilon greater than 0 is arbitrary. We then need to show that there exists a capital N in R such that for all little n in n, n bigger than capital N implies S sub n minus 1 is less than epsilon. So now we're proving, and now we're in an existential proof. We're trying to prove there exists a capital N. So we'll set up our two columns. We need to first find a capital N, and then we need to verify that our n satisfies the domain and propositional function conditions. To find capital N, first note, for all little n in n, S sub n minus 1 is equal to 1 plus minus 1 to the n over n minus 1. That's the expression for S sub n. And the 1's cancel, and we're left with the absolute value of minus 1 to the n divided by n. And the absolute value of minus 1 to the n is just going to be 1. And n is also a positive integer, so the absolute value of n is just n. So this is going to be equal to 1 over n. Now we want S sub n minus 1 to be less than epsilon. So first note that 1 over n is less than epsilon if and only if little n is greater than 1 over epsilon. We can see this if you multiply both sides of the inequality on the left by n and divide both sides by epsilon, we'll obtain the inequality on the right. Now we're going to be doing these types of manipulations on inequalities pretty frequently, and so if you just look at it, you can sort of see what we're doing is we're switching the little n and the epsilon. And this can all be verified rigorously using the order axioms. So now, this last inequality has the form of the inequality little n greater than capital N in the hypothesis of the condition for capital N with capital N equal to 1 over epsilon. And so this suggests that we should choose our capital N to be 1 over epsilon. So now we've found our capital N and we are ready to verify that it satisfies our two conditions. And so for the first condition, we can say that since epsilon is greater than 0, then capital N is equal to 1 over epsilon is obviously a real number. And for our second condition, we need to verify the propositional function. So we're going to suppose that little n is an arbitrary natural number. Suppose the hypothesis little n is greater than capital N. And we need to show the conclusion s sub n minus 1 is less than epsilon. Now from the work on the left, we showed that s sub n minus 1 is equal to 1 over n. Since little n is greater than capital N, then s sub n minus s, or 1, is equal to 1 over n, is going to be less than 1 over capital N, and we chose our capital N to be 1 over epsilon, so this is going to be 1 over epsilon. And now 1 over epsilon, the epsilon flips up in the numerator, and this just becomes epsilon. And so that's what we wanted to show. So this proves the propositional function holds, and this proves the existential statement, and thus the limit as n tends to infinity of s sub n for the sequence is 1. And so that's how we prove the limit of this sequence using the definition. Now let's examine how this proof was done. For the proof, we need to find a capital N that satisfies our propositional function. For all little n and n bigger than capital N implies s sub n minus 1 is less than epsilon. We started by evaluating s sub n minus 1, which appears in the conclusion of the conditional in the propositional function. For the conclusion, we need s sub n minus 1 equal to 1 over n less than epsilon. This holds if and only if little n is greater than 1 over epsilon, which looks like the hypothesis with capital N replaced by 1 over epsilon. And this tells us what we should choose for capital N. So what we're doing is we're starting with our conclusion, which is our s sub n minus 1, and we want this to be less than epsilon, and we're manipulating this to obtain an inequality that looks like our hypothesis, little n greater than capital N. And once we do that, we can usually read off what our capital N is. We can follow a similar procedure in general for these types of proofs. Our goal is to transform the inequality we need in the conclusion to look like the inequality in the hypothesis. We can then read off what we should choose for capital N. When we carry out this procedure, it may seem as though we're assuming what we're trying to prove, which we actually are to a certain extent. It's okay, however, to use the conclusion to find capital N as long as we complete the verification part of the proof. For another example, let's let s sub n be the sequence defined by s sub n is equal to 3n plus 1 divided by n plus 2 for each n in n. And for this sequence, we want to prove that the limit of s sub n as n tends to infinity is equal to 3. And again, to show this, we need to show the condition in the definition is true. For all epsilon greater than 0, there exists a capital N in R, such that for all little n in n bigger than capital N implies s sub n minus our limit, which is 3, is less than epsilon. So to start the proof, we'll suppose epsilon greater than 0 is arbitrary, and we need to show there exists a capital N in R, such that for all little n in n bigger than capital N implies s sub n minus 3 is less than epsilon. And now we're proving existence, so we're going to set up our two columns. So we need to first find a capital N, and then we need to verify that our capital N satisfies our two conditions. So once again, we'll start by looking at S sub n minus 3, which is the expression that appears in the conclusion, and we can say for all little n in n, S sub n minus 3 is equal to 3n plus 1 over n plus 2 minus 3. And if we put the two terms over a common denominator of n plus 2, we can simplify this and we'll obtain the absolute value of negative 5 over n plus 2. Well, the absolute value of negative 5 is just 5, and since n is a positive integer, n plus 2 will be positive, and so the absolute value of n plus 2 is just n plus 2, so this is going to be equal to 5 over n plus 2. Now, before continuing further in this proof, we want to examine how this proof differs from that in the previous example. In the previous example, at this point in the proof, we obtained S sub n minus 1 equal to 1 over n. We then said 1 over n is less than epsilon if and only if n is bigger than 1 over epsilon. And since the inequality little n greater than 1 over epsilon looks like the inequality little n greater than capital N in the hypothesis, this tells us to choose capital N is equal to 1 over epsilon. In this example, we have S sub n minus 3 is equal to 5 over n plus 2. Now, if we had 5 over n instead of 5 over n plus 2, we could carry out a similar procedure. We would have 5 over n is less than epsilon if and only if little n is greater than 5 over epsilon. We could then choose capital N to be 5 over epsilon. So what we want to do in this example is to somehow replace the 5 over n plus 2 with 5 over n. While these two expressions are obviously not equal, we can say that since n plus 2 is greater than n, then 5 over n plus 2 will be less than 5 over n. And using this inequality, we can then determine capital N. So now we'll return to the proof using this idea. So once again, we have for all little n in n, S sub n minus 3 is equal to 5 over n plus 2. And since n plus 2 is greater than n, then 5 over n plus 2 is less than 5 over n. Then S sub n minus 3 will be less than epsilon if 5 over n is less than epsilon, which holds if and only if n is greater than 5 over epsilon. And again, this last inequality has the form of the inequality n greater than capital N in the hypothesis of the condition for n. And this suggests we should choose capital N to be 5 over epsilon. So now we've found our capital N and we're ready to verify that it satisfies our two conditions. So first, since epsilon is greater than 0, then capital N equal 5 over epsilon will be a real number. So our domain condition is satisfied. For the propositional function, we'll suppose that little n in n is arbitrary. Suppose the hypothesis little n is greater than capital N. We then need to show the conclusion S sub n minus 3 is less than epsilon. From the work on the left, we know that S sub n minus 3 is less than 5 over n. And since little n is greater than capital N, then S sub n minus 3, which is less than 5 over n, will be less than 5 over capital N, and capital N we chose to be 5 over epsilon, so 5 over capital N will be 5 over the quantity 5 over epsilon. Okay, well the two 5's will cancel, the epsilon will flip up in the numerator, and this equals epsilon. And so this shows that our propositional function is true, and this proves the existential statement, and so we can conclude that the limit as n tends to infinity if S sub n is equal to 3. And we can follow the procedure outlined in these two examples for proving the limit of pretty much any sequence. In general, after evaluating S sub n minus s, we want to obtain an inequality of the form S sub n minus s is less than or equal to a over n for some constant a. Then S sub n minus s will be less than epsilon if a over n is less than epsilon. which will hold if and only if little n is greater than a over epsilon. We can then choose capital N to be a over epsilon. For another example, let's let S sub n be the sequence defined by S sub n is equal to n plus 2 over n squared minus 3 for each n in n. And we want to prove in this case that the limit as n tends to infinity of S sub n is equal to 0. So we need to show for all epsilon greater than 0 there exists a capital N in R such that for all little n in n, little n greater than capital N implies S sub n minus 0 is less than epsilon. So to start the proof, we'll suppose epsilon greater than 0 is arbitrary, and we need to show there exists a capital N in R such that for all little n in n, n greater than capital N implies S sub n minus 0 is less than epsilon. So now we're proving existence of a capital N. So ordinarily we would set up our two columns, but the calculations to determine capital N in this example are fairly long, so instead of writing this using the two-column format, we'll just write each part separately. So first we need to find a capital N. So we can say for all little n in the set of natural numbers, the absolute value of S sub n minus 0 is just the absolute value of n plus 2 over n squared minus 3 minus 0, which is equal to just the absolute value of n plus 2 over n squared minus 3. Now we want to get rid of the absolute values here. Now n is a positive integer, so n plus 2 will also be positive, and so the absolute value of the numerator, n plus 2, will just be n plus 2. However, n squared minus 3 could be negative. Well, it's only going to be negative when n is equal to 1. As long as n is bigger than or equal to 2, n squared minus 3 will be positive, and the absolute value of n squared minus 3 will just be n squared minus 3 in that case. So we can say when n is greater than or equal to 2, n squared minus 3 is greater than 0. So the absolute value of n squared minus 3 is just n squared minus 3. And then for all n greater than or equal to 2, we can drop the absolute values so that S sub n minus 0 absolute value is just n plus 2 over n squared minus 3. Now we want to obtain an inequality of the form S sub n minus 0 is less than or equal to a over n for some constant a. In order to do this, we first determine separate inequalities for the numerator and denominator of the forms the numerator will be less than or equal to bn, and the denominator will be greater than or equal to cn squared for some constants b and c. We'll then be able to combine these inequalities to obtain an inequality for S sub n minus 0 of the required form. For the numerator, since little n is a positive integer, then we know that 2 is less than or equal to 2n, which implies that our numerator, which is n plus 2, will be less than or equal to n plus 2n, which is equal to 3n. So this is an inequality of the required form. It looks like a constant times n. Determining an inequality for the denominator is a little trickier. We want an inequality of the form the denominator is n squared minus 3 is greater than 1/2 n squared. This holds if and only if 1/2 n squared is greater than 3. Just take the 1/2 n squared over to the left side and the minus 3 over to the right side. And this in turn holds if and only if n squared is greater than 6, which holds if and only if n is greater than or equal to 3. Or equivalently, n is strictly greater than 2. So if we suppose that n is greater than 2, then the denominator, which is n squared minus 3, will be greater than 1/2 n squared. We now have the two inequalities. Our numerator, which is n plus 2, is less than or equal to 3n, and the denominator, which is n squared minus 3, is greater than 1/2 n squared. The inequality for the denominator implies that 1 over n squared minus 3 will be less than 1 over 1/2 n squared. We can now combine this with the inequality for the numerator to obtain an inequality for the fraction. So s sub n minus 0 absolute value, which is n plus 2 over n squared minus 3, will be less than 3n, that's the bound for our numerator, over 1/2 n squared, which is the bound for the reciprocal of the denominator. And we can flip the 1/2 up in the numerator and cancel one of the n's, and we obtain 6 over n. So then s sub n minus 0 will be less than epsilon if 6 over n is less than epsilon, which holds if and only if n is greater than 6 over epsilon. So now this is an inequality of the form in the hypothesis of our conditional. So this has the form little n greater than capital N, which suggests that we should choose capital N to be 6 over epsilon. Recall, however, that in order to obtain the inequality for the denominator, we needed to suppose that little n was strictly greater than 2. This means we need to choose our capital N so that capital N is greater than or equal to both 2 and 6 over epsilon, and we can write this as capital N is equal to the max of 2, 6 over epsilon, where max means n equals whichever of the two numbers is larger. Note that since capital N is the larger of these two numbers, then capital N will be larger than both of them, so that capital N is greater than or equal to 2 and capital N is greater than or equal to 6 over epsilon. Okay, we're now ready to verify that our choice of capital N satisfies the domain and propositional function. So we need to verify that capital N, first off, for the domain is in R. And since epsilon is greater than 0, then 6 over epsilon is a real number. And since 2 is also obviously a real number, then capital N, which is the max of those two numbers, will be a real number. So our domain condition is satisfied. And for the propositional function, we need to verify that for all little n and n bigger than capital N implies s sub n minus 0 is less than epsilon. So we suppose little n in n is arbitrary. We suppose that little n is greater than capital N, and we need to show that s sub n minus 0 is less than epsilon. Now, since little n is greater than capital N, which in turn is greater than or equal to 2, then we know that little n is strictly greater than 2, so that little n should be greater than or equal to 3, which implies from our work above that s sub n minus 0 is less than 6 over n. Also, since little n is greater than capital N, which is greater than or equal to 6 over epsilon, then we know that s sub n minus 0 is strictly less than 6 over little n, which will be less than 6 over epsilon, and the epsilon will flip up in the numerator, the 6's will cancel, and this equals epsilon. So this verifies our propositional function, and this proves the existential statement, and we can conclude that the limit as n tends to infinity of s sub n is equal to 0. Okay, now this is about as complicated in an example as you're going to encounter. So here are a couple comments about this example and about these types of problems in general. In order to determine an n, we wanted an inequality for the denominator of the form n squared minus 3 greater than cn squared for some constant c. So we use the inequality n squared minus 3 greater than 1/2 n squared with c equal to 1/2. Now there's nothing special about 1/2. We could have used any value of c less than the coefficient of the n squared term, which was 1. So for instance, we could have used the inequality n squared minus 3 is greater than 1/4 n squared. The subsequent calculations would have been different, resulting in a different choice of capital N, but this choice will still work. The inequalities we obtain for the numerator and denominator both depend upon whether we have sums or differences in each. For instance, the numerator in the example was n plus 2, which allowed us to use the the inequality n plus 2 is less than or equal to n plus 2n, which is equal to 3n. If the numerator had been n minus 2, then we could have used the inequality n minus 2 less than n. Similarly, if the denominator had been n squared plus 3 instead of n squared minus 3, then we could use the inequality n squared plus 3 is greater than n squared. It would have been a little bit easier. Next, we want to examine divergent sequences. Given a sequence S sub n and a real number s, to show that S sub n does not converge to S, we need to show that the negation of the statement in the definition is true. This negation is, there exists an epsilon greater than 0 such that for all capital N in R, there exists a little n in N such that little n is greater than capital N, and the absolute value of S sub n minus S is greater than or equal to epsilon. So we need to prove that there exists an epsilon greater than 0 such that for all real numbers capital N, there exists a natural number little n such that little n is greater than capital N and S sub n minus S is greater than or equal to epsilon. Note this only shows that S sub n does not converge to S and does not show that the sequence diverges. Presumably the sequence could converge to some other number. To show that the sequence diverges, we would need to show that for all little s in R, S sub n does not converge to S. So that S sub n does not have a limit for any real number S. We could carry out the above procedure for an arbitrary real number S to prove the sequence diverges. However, this procedure will generally be fairly tedious, and often a better approach is to use a proof by contradiction. So to prove that a sequence diverges, we're going to use a proof by contradiction. We'll first suppose the sequence converges to a limit S for some real number S. We need to be careful here now. We can assume S exists, but we cannot assume a specific value for S. We're assuming the limit exists, but we don't know what the actual limit is. And in fact, the limit is not going to exist. Since we're supposing S sub n converges to S, then the statement in the definition, for all epsilon greater than 0, there exists a capital N in R, such that for all little n in N, n bigger than capital N implies S sub n minus S is less than epsilon, is assumed to be true. We then want to choose a specific epsilon greater than 0, which will be determined by this specific sequence. We can then conclude there exists a real number capital N, such that for all little n in N, n bigger than capital N implies S sub n minus S is less than epsilon. That is, all terms of the sequence past the capital Nth term are within epsilon distance of the supposed limit little s. We then need to obtain a contradiction using this conclusion. For an example of how we follow this procedure, let's look at the sequence S sub n defined by S sub n is equal to 1 plus minus 1 to the n for each n in N. We want to prove that S sub n is divergent. So when n is odd, minus 1 to the n is minus 1, and when n is even, then minus 1 to the n is just plus 1. Then the odd subscripted terms in the sequence will be 0, while the even subscripted terms are 2. So the sequence is going to be 0, 2, 0, 2, 0, 2. And we can see that it bounces back and forth between 0 and 2. So the sequence, since it oscillates between 0 and 2, the terms are never approaching a single value. So it certainly appears to be divergent. To prove it's divergent, we'll use a proof by contradiction. So we'll suppose the sequence does converge to some limit s. We then need to derive a contradiction. Since the sequence converges to S, then for any real number epsilon greater than 0, there exists a real number capital N such that for all little n in N, n bigger than capital N implies S sub n minus S is less than epsilon. Now keep in mind, we're supposing that the sequence converges to some limit S, but we don't know what S is, and in fact, S doesn't really exist. So we can't assume a specific value for S. What we are going to do is we're going to choose epsilon to be 1/2. And we'll see the motivation for choosing this value of epsilon as we go through the proof. Since we're assuming the sequence converges to S, then there exists a capital N in R such that for all little n in n bigger than capital N implies S sub n minus S is less than 1/2. This means that all sequence terms past the capital Nth term must be within epsilon equal 1/2 units of S. So if we choose a little n bigger than capital N, we can then conclude that the nth term S sub n must satisfy the inequality in the conclusion S sub n minus S absolute value is less than 1/2. So let's suppose that little n is an odd integer such that little n is greater than capital N. Since little n is greater than capital N, then S sub n must satisfy the inequality in the conclusion S sub n minus S absolute value is less than 1/2. Now since we suppose that n was odd, then we know that the sequence term S sub n is equal to 0. And the inequality simplifies to the absolute value of 0 minus S, which will just be the absolute value of S, is less than 1/2, which is equivalent to minus 1/2 is less than S is less than 1/2. So this hypothetical limit S that doesn't really exist has to be between minus 1/2 and 1/2. Now suppose little n is an even integer such that little n is greater than capital N. Since little n is greater than capital N, then the sequence term S sub n must satisfy the inequality in the conclusion again, S sub n minus S absolute value is less than 1/2. But now since little n is even, the nth sequence term S sub n is equal to 2. And the inequality is absolute value of 2 minus S is less than 1/2. And this is equivalent to minus 1/2 less than S minus 2 is less than 1/2. And then if we add 2 to all three sides of this inequality, we obtain 3/2 is less than S is less than 5/2. So this shows that our hypothetical limit S, which again really doesn't exist, must be between 3/2 and 5/2. So we've now shown that S is both between minus 1/2 and 1/2 and between 3/2 and 5/2. Well, this gives us a contradiction. So for instance, we can say that R and not R is equal to S is less than 1/2 and S is not less than 1/2. So since S is between minus 1/2 and 1/2, it must be less than 1/2. And since S is between 3/2 and 5/2, then S is not less than 1/2. It's in fact greater than 3/2. And since we obtained a contradiction, this tells us that our sequence diverges. Now, why did we choose epsilon to be 1/2 for this proof? What we needed was an epsilon so that the intervals obtained from the inequality S sub n minus S absolute value less than epsilon for the odd subscripted terms and the even subscripted terms of the sequence did not overlap, so that we obtained a contradiction. Since the sequence terms alternated between 0 and 2, choosing an epsilon less than or equal to half the distance between 0 and 2 will guarantee the intervals do not overlap. So for instance, instead of choosing epsilon to be 1/2, we could choose epsilon to be 3/4 or epsilon to be 1/3 or 1/4, and we would obtain a contradiction again.